Measures of central tendency. In samples as well as in populations, one generally finds a preponderance of values somewhere around the middle of the range of observed values. The description of this concentration near the middle is an average to the layman and a measure of central tendency to the statistician. It is also termed a measure of location, for it indicates where among all the possible values of a variable the sample or population is located. Various measures of central tendency are useful parameters in that they describe a property of populations. This chapter discusses the characteristics of these parameters and the sample statistics which are good estimates of them. The most widely used measure of central tendency is the arithmetic mean, usually referred to simply as the mean. Each measurement in a population may be referred to as an xi. Thus, one measurement might be denoted as x1, x2, and so on and so forth. The subscript I here might be any integer value up through n, the total number of xi values in the population. The mean of the population is denoted by the Greek letter mu. This is for the population and is calculated as the sum of all the xi values divided by the size of the population. So the formula for this is mu equals to the summation of xi divided by the population. I equals to 1 through n. So this is the calculation abbreviated concisely by this formula. The Greek letter sigma means a summation. Okay, so this means the summation of all xi values from x1 to the xn. The most efficient, unbiased, and consistent estimate of the population mean mu here is the sample mean, denoted by x bar, whereas the size of the population, which we generally do not know, is denoted as n. The size of a sample is indicated by small n. So x bar is calculated as a summation for xi over n, which is read the sample mean equals the sum of all measurements in the sample divided by the number of measurements in the sample. Example 5.1 here demonstrates the calculation of the sample mean. Note that the mean has the same units of measurement as do the individual observation. So the summation of xi here is equals to 95. So the total numbers, you sum up all of these, it will be 95, and the number of population and the number of sample is 24. So x bar is equal to summation of xi over n will be 95 over 24 equals 3.96 centimeter. You may pause the video and try it yourself. For the ease of data manipulation, it is often convenient to record data in the form of a frequency table, as in example 5.2. Then xi can be said to denote each different measurement, and fi here can denote the frequency which that xi occurs in the sample. So the sample mean may then be calculated as x bar or equals to the summation of the frequency of fi, the number of sample xi over n. Okay, which means that in this case the summation of fi will equals to n and equals, which means equals to 24. So x bar equals to the summation of fi xi over n. So fi xi means that this formation, so you multiply 3.3 times 1 here, so which is the frequency here, then will be 3.3 and so on. So you calculate, and all of this, the summation of all this will get 95. So again, similarly, so this will be 95 over 24. Same answer like before, 3.96. So if data are plotted as a histogram like this figure 5.1, the mean is the center of the gravity. The mean is the center of the gravity here. Change the color a little bit. Okay. The center of gravity of the histogram. That is, if the histogram were made of a solid material, it will balance horizontally. So it will be balanced between left and right. So this is mean will be in the middle. That is, if it will balance horizontally with the fulcrum at x bar. The mean generally is applicable only to ratio or interval scale data. Next is the median or other quantiles. The median is the middle measurement in a set of data. That is, there are just as many observations larger than the median as there are smaller. The sample median is the best estimate of the population median. In a symmetrical distribution like this one and this one, the sample median is also an unbiased and consistent estimate for population mean, but it is not as efficient as statistics as sample mean, and should not be used as a substitute for sample mean. If the frequency distribution is asymmetrical like this, the median is a poor estimate of the mean. The median of a set of data is readily found by first arranging the measurements in order of magnitude, either increasing or decreasing, as is done with the sample for the species A and species B. So the median is equals to xn plus 1 divided by 2, only if the n is an odd number. So let's say here will be odd number 1, 2, 3, 4, 5, 6, 7, 8, 9. So for this data, so the median for this data is x 9 plus 1 divided by 2, which means that x number 5. So the median will be the value, the number 5 value. So this is 1, 2, 3, 4, 5. So the median will be 40 for this sample, because this is an odd number of sample. However, if n is even, like this sample, this is even number, okay, then the median is defined as the midpoint between the two middle measurement. That is, the median here, for the median, the formula for the even number is median will be xn divided by 2 plus x n divided by 2 plus 1 divided by 2. So this x n plus 2, will be this is all total is 10. So x5, so 10 divided by 2 equals to 5, x5. So this 10 divided by 2 plus 5 plus 1, so x will become 6. So this will be x5 plus x6 divided by 2. x5 is 1, 2, 3, 4, 5 is 40. So plus x number 6 will be 41. So this is divided by 2. 40, 81 divided by 2 equals 40.5. So the median for these samples will be 40.5. So somewhere in the middle here. The mode is commonly defined as the most frequently occurring measurement in a set of data, but it is perhaps better to define a mode as a measurement of great concentration, for some frequency distributions may have more than one such point of concentration, even though these concentrations might not contain precisely the same frequencies. Thus, a sample consisting of this following data here would be said to be bimodal, the two modes being 8 and also the 12 here. Some authors would refer to 8 as the major mode and call 12, this is the major mode, and the 12 will be the minor mode. A distribution in which each different measurement occurs with equal frequency is said to have no mode. When you have similar frequencies of all these data, it means that they have no mode. If two consecutive values of x have frequencies great enough to declare the x values modes, the mode of the distribution is said to be the midpoint of these two axes. For example, the mode for this 3, 4, 7, 7, 8, 8, 8, 10 is 7.5 here, because you have similar 7 and same number of 7, similar number of 8 is equal, then you can divide by 2 is 7.5. The sample mode is the best estimate of the population mode. When we sample a symmetrical unimodal population, the mode is an unbiased and consistent estimate of the mean and median, but is relatively inefficient and should not be so used. As a measure of central tendency, the mode is affected by the skewness less than is the mean or the median, but is very much more affected by sampling than these other two measures. The mode, but neither the median nor the mean, may be used for data on the nominal as well as the ordinal, interval, and ratio scales of measurement. In a unimodal asymmetric distributions, the median lies about one-third the distance between the mean and the mode. The mode is not often used in biological research, although it is often interesting to report the number of modes detected in a population if there are more than one. There are also other measurements of central tendency which I will not cover in this lecture. These include the range midpoint or mid-range. There is also called a geometric mean or harmonic mean. You can find this information in your textbook.